Good morning and welcome to the last page of section 3.2, where we're still talking about the logistic equation, but here we've added in an h, either plus h or minus h, depending upon if we're adding to or subtracting from the population. So I'm going to go ahead and solve for example 2, which is question 6 in the text, based off of question 5. So question 6, investigate the harvesting model in problem 5, both qualitatively and analytically. In the case A equals 5, B equals 1, H equals 25 over 4. Determine whether the population becomes extinct in finite time. If so, find that time. So they go ahead and they give us the logistic equation in 5, which is going to be dP over dt equals P times A minus BP minus H, where our initial P is P sub 0, the initial population. So the first thing that we're going to do is we're going to draw a phase portrait to see, based off of our differential equation, where our differential equation is tending to, because if we're tending toward a certain population, then that kind of tells us, what the carrying capacity would be, and if we are above or below this initial starting point, will we eventually become extinct. And so, starting off with the phase portrait, all I did was I substituted in for A and B. So A was 5, B was 1, and H was 25 over 4. So I just did all my substitutions there. And then I'm going to go ahead and set this differential equation equal to 0, define my critical values. So I do that, I distribute the P, and then after I've distributed the P, I get P squared minus 54P plus 25 over 4. Notice that all the signs changed because I multiplied by a negative 1 throughout the equation, and then I just reordered all my terms. Now after that, I decided to multiply through by 4 so that I get this quadratic equation on the left side. 4p squared minus 20p plus 25 equals 0. That way I could factor that. Now when I factor that, I get 2p minus 5 times 2p minus 5 equals 0. So 2p minus 5 squared is equal to 0. So my critical value would be p equals 5 over 2. So now I go ahead and I draw the phase portrait over there to the right. Now I'm going to plug in some values. I know that 5 halves is a critical value, and then so I'm going to plug a number greater than 5 halves, so I plug in 3. When I plug 3 in, I plug it into the initial differential equation, so the logistic equation. I get 3 times 5 minus 3, which is 2. That's 6. 6 minus 25 over 4 is going to be negative 1/4. So anything that is above 5 halves is going to be tending towards 5 halves. When I plug in anything below 5 halves, I can plug in 0, I could plug in 1, 2. And I plug in 0 because it's, easy to work with. You kind of really don't want to plug in anything less than that because we're talking about population, that can be less than 0. But when we plug in the value, we're going to get, again, we plug it into the logistic equation, we're going to get, still a negative number. So we're tending down. If we plugged in 1, if we plugged in 2, we'd get a negative number. So anything that's below 5 halves is going to tend towards 0. So here's my phase portrait. Any number above 5 halves is going to tend towards 5 halves. Any number that's less than 5 halves is going to tend towards 0. So what we say is if P of 0, so if our initial population is less than 5 halves, our population is going to become extinct. All right. So that kind of answers the first part. Now what we want to do is we want to find out, okay, well, when will the population become extinct in finite terms? So to do that, we need to solve for the logistic equation. We got to find the initial solution. All right. So we're going to take our differential equation and we're going to solve. So we're going to create separation of variables. So the first thing that I've done was I've got a common denominator over here so that I could bring it all to be one term. And so once I get a common denominator, multiply it by 4, bring it together. That's going to be the numerator. The denominator is 4. And now I'm going to go ahead and move this over to the left-hand side. And so I'll divide that. I'll put the dt on the right-hand side. So I'm using separation of variables. Now, once I've done that, I'm going to take the integral of the left side and the right side. Doing the integration on the right, it's pretty simple. 1/4 t plus c. The integration on the left, though, I'm going to pull out the negative, and I'm going to be left with 4p squared minus 20p plus 25. And I recall from when I was doing the phase portrait that that's just 2p minus 5 squared. All right, so when I solve for this, I'm not going to have to worry about partial fractions because it's 2p minus 5. I can do u substitution, where I simply have dp over u squared, or the better way, u to the negative 2 dp. So then I'm able to integrate that way. And when I integrate that way, I realize, okay, derivative of 2p minus 5 is 2, so we need a 2 out in front, so I need to get rid of that 2. So I'm going to have a 1/2 out in front. The negative's going to cancel out with the negative. So then I'm just left with... So when we integrate this left-hand side, we're just going to get 1 over 2p minus 5. I'm sorry, 1/2. I was wondering where that 2 went. 1/2 2p minus 5 to the negative 1. All right, now we're going to go ahead and we got to solve for p because we got to find our solution to the differential equation. So let's get rid of this 1/2 by multiplying everything by 2. So we multiply everything by 2, we get 1/2 t plus c. All right, after we multiply everything by 2, I'm going to put 2p minus 5 in the denominator. All right, now one thing I can do over here on the right is I'm going to write this as one term. The reason why is because I'm going to invert the left side and the right side. So I can get a like term, so c is just going to be c over 2, and combine that together, so it's going to be t plus c over 2. So now that I have a fraction is equal to a fraction, I want the p in the numerator. I'm just going to invert both sides, and so I have 2p minus 5 on the left. Flip t plus c over 2 to become 2 over 2 plus c. And now we're going to solve for p. Subtract 5, divide by 2. When I get rid of this minus 5, I add 5. And then when I get p by itself, I got to divide everything by 2. 2 divided by 2 is going to be 1. And then 5 divided by 2 is going to be 5/2. And so now we've solved for p. So here's our solution. P of t is equal to 1 over t plus c plus 5/2. We want to solve for c, though. All right? C is a constant. We got to find that constant. Now, one thing that we know based off the initial condition is that p of 0 is equal to p sub 0, or p naught. So p of 0, since p of 0 is equal to p sub 0, that's going to be equal to, just 1 over 0 plus c plus 5/2. All right, you think, okay, it's not going to be too bad. And so we solve, we get 1 over c. This is going to become 1 over c. We're going to get rid of plus 5/2 by subtracting 5/2 to the left side. So p sub 0 minus 5/2 equals 1 over c. Get another common denominator so that we can have a fraction. So we multiply p sub 0 by 2 over 2, and we get 2p sub 0 minus 5 over 2. Since that equal to 1 over c, invert both sides, and we've solved for c. C is equal to p over 2 times p sub 0 minus 5, or p naught. Oops, I think I did that too many times. All right. So now that we've solved for c, we're going to plug that back into our equation, and when we do that, we're going to get and make sure I'm not accidentally erasing too much. Over here on the right. So all we did was we substituted in for our c value. All right. And we got that 2 over 2 times p sub 0 minus 5. Now, what we want to do is we want to write this a little bit better. We don't want to have a fraction within a fraction. So we're going to multiply this whole term right here by 2p sub 0 minus 5 over 2p sub 0 minus 5. So the numerator, oh, don't want to do that. So the numerator is going to be multiplied by 2p sub 0 minus 5, and that's how we get that. And then the entire denominator is going to be multiplied by 2 times p sub 0 minus 5. That's going to take care of this fraction, and we're just going to be left with 2. But then we have to multiply t times p sub 0 minus 5, and that's how we get that. So this is how we've gotten this equation right here. All right, plus 5 halves. Now, again, we have two fractions added. Let's get a common denominator. So what we're going to do is we're going to multiply 5 halves times this denominator. So then we have 5 times t times 2 p sub 0 minus 5 plus 2. That's just going to give us this term right here, where we just multiply 2p sub 0 times 5, which gives us 10. P sub 0 minus 5 times 5, which is 25, and then 2 times 5 is 10. And then on the bottom, we multiply. We need a 2 over here, so we need a 2 times that. So we're going to multiply 2 times 2, which is 4p sub 0 minus 10. So there's all the multiplication, and in the bottom we have the common denominator. All right, now we're going to simplify. We notice that minus 10 plus 10, they're going to cancel each other out. And then we're left with, 4p sub 0 plus t times p sub 0 minus 25. So that's the numerator, right? Then the denominator, all I'm going to do to simplify that, I'm going to just distribute that in the inside of the parentheses. So that's how I get 4p sub 0 minus 10 plus 4, just distributing that too. And then there's their solution for p sub 0, all right? So that's the logistic function. Now that we found the logistic function, we're going to find, okay, when will our population become extinct for p sub 0 less than 5 halves? Again, if our initial population is greater than 5 halves, we're good. It's not going to become extinct. But if it's less than 5 halves, we are going to become extinct. And you can see that based off the phase portrait. Now, what we're going to do is we're going to solve where our population is equal to 0. So when does that occur? We're going to solve for t. So we're going to set our logistic function equal to 0, and we're going to solve. Now, because it's a fraction and set equal to 0, that denominator cannot equal 0, so that denominator goes away. That's not what's going to give us 0. The numerator is what's going to give us 0. So on top, we're going to go ahead and set all that equal to 0. Get rid of the p sub 0, 4p sub 0 by subtracting. That's how I get minus 4p sub 0. And then we're going to divide by 10p sub 0 minus 25 because that's multiplying t. And there's our solution. So it becomes extinct when time is equal to negative 4 times the initial population divided by 10 times the initial population minus 25. All right? And again, you can clean that up. You can rewrite that if you want to say or, and we can make this t is equal to 4p sub 0 over 25 minus 10p sub 0. So where you don't have to really look at it like a negative. Again, you don't have to write it this way. It's just me oversimplifying. You can just keep it as terms of t. And again, I went ahead and just went over all this because it was going to take a long time for you to sit through me writing all this out, because this is a very long problem. But that's it. And that's it for section 3.2. And I hope that you enjoyed 3.2 with modeling. And now we're going to go over to high